Hello everyone, thanks for your interest in our paper. I am Jawad Mehr and I will be presenting our paper on intelligent control of lower limb exoskeletons. Over this presentation, I will introduce importance of exoskeletons in the rehabilitation applications and then describe our motivations for this research. Then the methods introduced in this research will be described and also be evaluated by the experimental results in the next part. Finally, the concluding remarks will be presented at the end to give you the take-home message. First of all, we are interested in answering this question. What are the advantages of employing exoskeletons in the rehabilitation goals? Several points can be mentioned for that. First, using exoskeletons, you can collect a comprehensive amount of data during different sessions of rehabilitation and can evaluate the progress based on that. Second, assistance level can be adjusted very easily via exoskeletons that is interesting in most of the rehab applications. Other points like remote rehabilitation for the areas with limited access to the clinics and possibility of social distancing between clinicians and patients during rehabilitation are reasons that makes using exoskeletons interesting in the most of rehabilitation goals. Most of the previous studies confirm that different people have different gait patterns. In other words, the amplitude, frequency, and range of motion for the joints change from one person to the other one. Even the gait pattern for one person can be affected and changed because of several reasons like aging or fatigue. However, most of the available exoskeletons in the market are using a predefined fixed trajectories. To provide a comfortable walking, it is important to reshape the exoskeleton trajectories to be adaptable with the human user. Postural stability is the ability to control the body in the space for the purpose of walking. As it can be understood from the definition, it is the key requirement in the bipedal walking. In order to provide safe locomotion for the exoskeletons, we should monitor the postural stability and any reasons that can lead to loss of that. For the case of using exoskeletons with the shapeable trajectories, change in the gait pattern is an important source that can lead to loss of the postural stability. Therefore, if the control strategy lets the user to change the gait pattern, it needs to monitor postural stability to prevent any unsafe action. Given all of the previous motivations, in this project we have proposed a shared autonomy that gives user enough authority to shape the gait trajectories to the desired values via adaptable CPGs. And at the same time, exoskeleton autonomously adjusts the upper body position to enhance postural stability via DCM. Therefore, the proposed method can provide a comfortable and safe locomotion for the exoskeleton user. The CPGs are a set of differential equations that can produce time-continuous rhythmic trajectories of motion. In this project, we have used CPGs to adjust gait parameters of the exoskeleton in order to provide the compatibility with the user's gait pattern. To this end, the adaptable CPGs were developed that uses human-robot interaction torque as input and adjusts the amplitude and frequency of gait based on that. Therefore, exoskeleton can adapt user's gait by monitoring the interaction torque. In this part, the mathematical formulation of the proposed adaptable CPGs will be described. Data from an offline training session was collected and fed to a neural network to capture the passive dynamics of the human exoskeleton system. Therefore, given position and velocity of each joint, the passive torque was estimated by the trained network in the real time. During the experiment, the difference between the measured torque by the joint encoders and the estimated passive torque by the neural networks was calculated as active human-robot interaction. Then, the interaction energy was calculated as time integral of the multiplication of active interaction torque and joint velocity. Given the interaction energy, the adaptable CPG dynamics was developed as this equation. The energy terms are added to the classical CPG dynamics in order to apply effects of interaction into the exoskeleton trajectories. Also, the threshold terms were used for the first time in order to limit the amplitude and frequency to the safe values. Given the amplitude, frequency, and phase of walking from adaptable CPG dynamics, the updated trajectories of the exoskeleton joints will be determined by this equation. By applying any change to the joint trajectories, the postural stability needs to be monitored. For that goal, the DCM analysis was employed. The divergent component of motion, or DCM, is a common method in monitoring postural stability of bipedal humanoid robots. In this project, we have tailored the DCM method to be usable for the exoskeletons. In the DCM analysis, we receive the velocity of walking as input and process that to determine the upper body position that best fits to the input velocity. The new formulation of the DCM analysis will be described in the next slides. The DCM model proposed for the bipedal robots needs to be improved to be usable for the exoskeleton applications. The linear inverted pendulum flywheel model was used in the DCM formulation for the humanoid bipedal robots. In this model, mass and inertia of each link considered to be zero and also the total mass of the system considered to be on the imaginary line connects two hips. This consideration needs to be relaxed in the new model to be a good fit for the human exoskeleton system. Therefore, we introduced the fourth-of-body model to consider mass and inertia for all of the links and also let the position of central mass to be at any point on the space. By considering the body to be close to the upright configuration, the dynamics of 4dB model was determined as this equation. Also, the position and acceleration of central mass are these equations, where phi and psi are defined as these two vectors. The elements of phi vector are functions of mass and position of central mass of links as presented here. Given the 4dB model dynamics and the formulation for the position and acceleration of central mass, the relation among acceleration and position of central mass and the applied torque to the upper body can be determined as this equation, where alpha, beta, and h are as presented here. Given the formulation in the previous slide, we introduced the DCM as the divergent part of motion of central mass and its dynamics as these equations. Designing an stable locomotion for DCM will guarantee stable locomotion for the central mass, and for that purpose, we need to specify the DCM position at the end of each step. To specify the DCM at the end of each step, we use the velocity of walking to determine the desired DCM offset at the end of each step. And a schematic of the DCM trajectory in the sagittal plane, DCM offset, and also footprints are shown in this picture. Given the desired DCM at the end of each step, the optimization problem was formulated as this equation to calculate the required upper body torque. Given the upper body torque, the upper body position correction was calculated based on this equation, and the calculated correction was applied to the hip joints of stance and swing legs to adjust the upper body positions. Given the desired trajectories of all joints from both CPG and DCM calculations, a PD controller was employed to track them and provide users desired walking. Here at this section, you can see some results of applying the proposed method on a human user wearing the indigo lower limb exoskeleton. This figure depicts the trajectory of right and left hip joints with and without DCM corrections. As it can be seen, at the beginning of the stance phase of each leg, the corrections has been applied to decrease the hip joint angle for that leg. It means that the exoskeleton has moved the upper body forward in response to the user's interaction and velocity increasing. Similar results can be seen in the synchronization between right and left hip joints. The dashed red line shows the trajectory without DCM corrections, and the blue solid one are the results of the DCM corrections. As it can be seen, as a result of the DCM correction, the synchronization of the right and left hips became distorted at the point of switch between stance and swing legs. This figure depicts the transition of the DCM in the absence of the upper body corrections. The red colors shows the results for the case that left leg is in the stance phase, and the blue one is the case that right leg is in the stance phase. As it can be seen, there is a considerable error between the DCM at the end of a step with the desired ones. This figure shows the results of transition of the DCM in the presence of the upper body corrections. In the presence of the corrections, the average error value have been decreased from 5 cm to 2 mm. Also, as it can be seen, the DCM has experienced more organized transitions when the corrections have been applied. In the next two figures, the effectiveness of the proposed adaptable CPGs in adjusting amplitude and frequency of walking will be studied. This figure shows the total amplitude with respect to the time. The user's applied interaction torque has increased amplitude from 1 to 1.19. At a time equal with 0.85 seconds, the amplitude has reached the threshold value, and the threshold term prevented passing the maximum safe value, which is equal with 1.2. This figure depicts the results for variation of the frequency with respect to the time. Similar to the results presented for the amplitude, the user's applied interaction has increased the frequency of walking and reached the threshold values at time equal with 2.17 seconds. Then the embedded threshold term prevented passing the saved maximum value. The results are shown in the solid blue line. In another experiment, the user has applied interaction and increased the frequency of walking and kept that level over several steps of walking. The results can be seen in the dashed red line. To wrap up, in this research we proposed a shared autonomy between human and exoskeleton in order to give the user enough authority to adjust the gait pattern of the exoskeleton. At the same time, the exoskeleton automatically adjusts the upper body position in real time to enhance the postural stability. The DCM method that was proposed for the bipedal humanoid robots tailored to be suitable for the exoskeleton applications. The results of the experiment on the human user wearing indigo lower limb exoskeleton showed that the proposed method can successfully adjust the gait pattern to the user's desired one and also control the position of upper body to enhance postural stability. At the end, I would like to appreciate the funding agencies for their support on this project and also thank you for your time.